Section 8.2, Vectors in the Coordinate Plane. In Lesson 8.1, you found the magnitude and direction of the resultant of two or more forces geometrically by using a scale drawing. Since drawings can be inaccurate, an algebraic approach using a rectangular coordinate system is needed for situations where more accuracy is required or where the system of vectors is complex. A vector OP in standard position, so here's OP in standard position, on a rectangular coordinate system can be uniquely described by the coordinates of its terminal point at P of xy. So we can describe this vector just by using xy. We denote OP on the coordinate plane by xy. This is in component form, and it has the chevrons instead of the parentheses. Notice that x and y are the rectangular components of OP. For this reason, xy is called the component form of a vector. Now, vectors don't have location. They only have they have length and they have direction. So saying that this vector is the vector 3, 2 is the same as saying this vector is 3, 2. It's really the same vector, even though it has a different location. Since vectors with the same magnitude and direction are equivalent, many vectors can be represented by the same coordinates. For example, vector P, T, V, and W, the ones we saw in the previous diagram, are equivalent because each can be denoted as just 3, 2. To find the component form of a vector that is not in standard position, you can use the coordinates of its initial and terminal points. And to find a vector in component form or in standard position, we just subtract the x's and we subtract the y's, and we always take the second point minus the first point. Here we have example 1. Find the component form of AB with initial point A at -4, 2 and terminal point at 3, -5. So when we find the component form, we're just finding from beginning to end, from initial to terminal point, the horizontal distance and the vertical distance. So if we start here at the initial point, we just count over 1, 2, 3, 4, 5, 6, 7. We have to go 7 to the right, and 1, 2, 3, 4, 5, 6, and 7 down. So we can represent this vector in component form as 7, -7. And that's like taking this vector, the original, and we're just moving it over so that the initial point is at 0, 0, and we'd have the component form 7, -7. Now, of course, if we have some very large numbers or decimals, we're not going to count. So the way we find this is we just take x2 minus x1, so 3 minus -4, and then y2 minus y1. We have -5 minus 2. So we just subtract the x's and the y's, and we get 7, -7. The magnitude of a vector in the coordinate plane is found by using the distance formula. So magnitude of a vector is like saying, like finding the length of the vector. If V is a vector with an initial point x1, y1, and terminal point x2, y2, then the magnitude of V is given by, it's the distance formula. It's just the length of the vector. And if we have a non-horizontal or non-vertical vector, we can always turn this into a right triangle. So here's our same vector that we worked out before. Well, really, we can just go 7 over and 7 down, and now we have this right triangle. So really the distance formula or the magnitude of a vector is just really the Pythagorean theorem. So the magnitude of vector V, if we want to call this vector V, or in this case, I guess it's magnitude of vector AB, is equal to the square root of, and we can take x2 minus x1, so 3 minus -4, and we're going to square that and add that to -5 minus 2 squared. So that's equal to the square root of, that's going to be 49 plus 49. So we have the square root of, let's see, we got 8 carry the 1, looks like 98. The square root of 98 is the length of this vector, or what we call the magnitude of the vector. Addition, subtraction, and scalar multiplication of vectors in the coordinate plane is similar to the same operations with matrices. If A is A1, A2, and B is B1, B2 are vectors and K is a scalar, then the following are true. To add two vectors, you add the x's and you add the y's. To subtract two vectors, you subtract the x's and subtract the y's. And if you're going to multiply a vector times a number, you can just multiply the x and the y components times that number. It's very straightforward. So let's try a couple here. Find each of the following for w equals -4, 1, y is 2, 5, and z is negative 3, 0. What if we just took w plus y? Well, w plus y is going to be negative 4 plus 2, negative 2, and 1 plus 5, which is 6. Very simple. Well, here we have z, which is negative 3, 0, and we're going to subtract 2 times y, which is 2, 5. And we're going to do order of operations, so we want to do multiplication first. Negative 3, 0, and then minus 4, 10. We're just going to multiply 2 times the x and 2 times the y. Negative 3 minus 4 is negative 7, and 0 minus 10 is negative 10. A vector that has a magnitude of 1 unit is called a unit vector. So if we did the Pythagorean theorem on this vector, on this unit vector, we'd have a length of 1. It is sometimes useful to describe a non-zero vector v as a scalar multiple of a unit vector u with the same direction as v. To find u, divide v by its magnitude v. So here we're going to find a unit vector u with the same direction as v equals negative 2, 3. So we want to find a vector that, let's just plot negative 2, 3. Negative 1, 2, 1, 2, 3. So this vector is not 1 unit long. So now what we want to do is find the terminal point, find in component form a vector that's the same direction but is only 1 unit long. Same direction as this one, 1 unit long. And to do that, we need to find the magnitude of this vector. So the magnitude of v is equal to the square root of 4 plus 9. So that's the square root of 13. So now u is 1 unit long in the same direction as this. Now here's how we're going to write it. This is going to be equal to negative 2 divided by square root of 13 and 3 divided by square root of 13. Now what if we did, now you don't have to do this, but what if we did the Pythagorean theorem or found the magnitude of this vector? It'd be the square root of. We'd have to square this, which would be 4 thirteenths when we square, and plus when we square this one, it would be 9 thirteenths, which is equal to the square root of 13 thirteenths, which is square root of 1, which is 1 unit long. So this vector is going in the same direction as the original one and is 1 unit long, so we call it the unit vector. The unit vectors in the direction of the positive x-axis and positive y-axis are denoted by I. So this would be a vector with 1 unit that goes perfectly horizontal or along the x-axis, and j goes along the y-axis, and it would be denoted as 0, 1. Now both of these vectors would be 1 unit long, respectively. Vectors I and j are called the standard unit vectors, and they're called the unit because, well, they're 1 unit long. These vectors can be used to express any vector v equals ab as ai plus b times j as shown in figure 8.2.4. So the vector ab can be written as ai plus b times j. The vector sum ai plus b times j is called a linear combination of the vectors I and j. So that's the terminology that we need there, linear combination. Example 5, write a vector as a linear combination of unit vectors. Let vector DE be the vector with initial point negative 2, 3 and terminal point 4, 5. Write DE as a linear combination of vectors I and j. Well, we need to get this vector into component form. So vector DE is equal to, we need 4 minus negative 2 and 5 minus 3. So this is equal to 6, comma 2. So now we can write this as 6i plus 2j. A way to specify the direction of a vector v equals ab is to state the direction angle theta that v makes with the positive x-axis. It's like the unit circle. From figure 8.2.5, it follows that v can be written in component form or as a linear combination of I and j using the magnitude and direction angle of the vector. So really we're just using unit circle stuff here. So if you want to write the x coordinate, it's just the magnitude of the vector times cosine, and the y coordinate is the magnitude of the vector times the sine. Now the magnitude of the vector is just like saying the radius of the circle. So this would be the radius of the circle, this would be the circle here, and we just multiply that times the angle. Now with the unit circle, our magnitude is 1. So this is really, on the unit circle, it'd be 1 times cosine of theta and 1 times sine of theta, but we don't write the ones because 1 times cosine is just cosine. Well, now if you change the radius, if the radius or the magnitude of the vector would be 2, you just take 2 times cosine of theta and 2 times sine of theta there to find the y-coordinate. Find component form. Find the component form of the vector v with magnitude 10 and direction angle of 120 degrees. So we're at 120 degrees, which is one of our pi over 3's. So this is negative 1/2 and then square root of 3 over 2. But that's if the radius was 1. Well, the magnitude of this vector is 10. So we have to take 10 times, and we're going to take the cosine of 120, which happens to be negative 1/2. So times negative 1/2, and then 10 times the square root of 3 over 2. So the component form of this vector is negative 5, comma, 5 square root of 3. It also follows from figure 8.2.5 on the previous page that the direction angle theta of vector v is equal to AB can be found by solving the trigonometric equation tangent of theta equals v sine over v cosine, or the tangent of theta is equal to b over a. So let's take this point right here, 3, 7. So 1, 2, 3, 1, 2, 3, 4, 5, 6, 7. Now what they're saying is, all right, if we want to find the angle right here, this angle, well, we can turn this into a right triangle. So this side is 3 and this side is 7. And then the tangent of the angle that we're looking for, this would be theta right here, is equal to 7 over 3. So now theta is equal to the inverse tangent of 7/3. So we can get out our calculator now. We're going to make sure the mode is in degrees. And we can do the inverse tangent of 7/3, and we find out that the degree angle is 66.8. So 66.8 degrees. And likewise, we have the r, the radius of the circle, is 4, -5. It's the vector 4, -5. So 1, 2, 3, 4, 1, 2, 3, 4, and 5. So we want to know this angle right there. So we grab our calculator, and now we're going to do inverse tangent of, it's y over x, so it's really -5 divided by 4 in this case. And we have -51.3, so -51.3 degrees.